Good morning. Now we have a talk by Professor Jaya Iyer. You may recall my mentioning her on first day in IWM presentation. She got the first, and under her leadership, there was a first project from NBHM for activities related to women in mathematics, and which followed a big conference that she arranged with Vaijayanti Chari in 2012 in IMSc, right? So her talk is Topological Invariants Arising in Geometry. She's a professor of mathematics, a professor at Institute of Mathematical Sciences, IMSc. Yeah, you're welcome to.
Thanks a lot, Riddhi. So I should really thank Riddhi for taking forward IWM. In fact, if I recall, in 2009, so she had, in India, I think we never had this conferences for women. And so I think in 2009 in Delhi, I guess, so she had initiated one program. And I think later, 2 years later, Vaijayanti had this idea to continue it. And I think after that, Riddhi and her team, in fact, really took it forward and continued it for several years. So thanks to Riddhi. Let's applaud her. Yeah, and so now I thank the organizers here for inviting me to speak here. And I again congratulate Sanoli for, and of course, the other members who have come from other countries, long distances, and have really put in a lot of efforts to take this purpose of supporting women in maths. So I thank all of you. So let's thank all of them again. Okay, so now let's come to the talk. So I would like to speak on the topological invariants arising in geometry. So this is something I started looking at maybe some 15 years ago. So I think I had this I was fortunate to be a postdoc in Europe, I think earlier, long time back, and Ellen Eno, so she introduced me to some nice topics on secondary classes, rather the Chern-Simons classes and their applications in algebraic geometry. And that prompted me to study further and actually looking at the origins of the questions. And so I think I would just like to introduce the way I think about these invariants, like how does it come in topology and why is it so relevant in geometry as well. So I would touch on these topics, and you're welcome to ask questions after the talk or during lunchtime. So I'm here till tomorrow, in fact, till Sunday, so you can catch me anytime. So topology, as we understand, so this is a study of spaces with the requirement that properties like stretching, bending, but not tearing are preserved. So we basically want to look at spaces. So the first examples that we come across when we are studying maths, I think in 12th standard or after that. So these are the Euclidean spaces. So as we can see that Euclidean spaces, so we are not looking at the vector space structure on these spaces, R, R2, R3, Rn, but rather the underlying topology of these spaces given by the metric function on them. So there is a nice topology, so which we call as the Euclidean topology. And now we want to look at the non-Euclidean spaces. So the first examples that we are taught are the circle, the sphere, the torus. And so these are some nice spaces, compact spaces sitting inside Euclidean spaces, and it attains a subspace topology. And this is what we start looking at and their properties. And now when we want to phrase, like in maths, we want to generalize everything, whatever we study in the basic examples. So to study such spaces, so we try to frame such properties. So okay, so now that we understand Euclidean spaces and we want to understand other spaces where you can carry forward most of the technology on Euclidean spaces to such spaces which don't look like R or Rn. So for that, we borrow good pieces from the Euclidean spaces and patch them together. So for instance, so the good pieces would be a point in 0 dimension, a unit interval in dimension 1, and then in higher dimensions, you look at the unit sphere or the unit balls. So these are what we call as the standard open cells in each dimension, in each Euclidean space. And so what do we do with all these spaces, all these basic units? So with these things, we can construct what we call as a finite cell complex. So that is, you can think of as in an abstract way as finite disjoint union of open cells of varying dimensions. So here just remember that I'm looking at finite cell complexes. So I would just look at finite number of cells in each dimension. And I would glue them together. So at least it will remember that you have in each dimension, there is some data coming from the standard Euclidean space. Okay, so now we construct, or rather think of our finite cell complex in this manner. And now for example, you can think of your circle. So this is going to be a disjoint union of an open interval and a single point. So that means a standard cell in dimension 0. And now you can think of your sphere as well as a disjoint union of a 2-dimensional open cell and a 0-dimensional cell, that is a point. And now similarly, you can look at your torus, a compact torus, as a disjoint union of 1, 2 cells. So that's the largest cell. And then you have 2 circles binding in either directions. So these are the 1-dimensional cells and the point where all of them are glued together. So now a basic invariant, because whenever you study topological spaces, you want to attach invariants to them, and invariants are useful because invariants helps us to classify or distinguish topological spaces or whatever objects you are looking at. So the first basic invariant is the dimension. So in this case, when you are looking at a finite cell complex, so you are going to look at the largest dimensional constituent cell of that complex. So for example, a circle, so the largest dimensional is the open interval, it's dimension 1. So that's what our intuition tells us. Now for a sphere, it's the open disk. So that's again 2-dimensional. And now even for a torus, it's the same thing, and so on. Okay, so this is, so dimension, it is a very coarse invariant because I think just by dimension you have, for example, a torus and a sphere. So they are again 2-dimensional, and it just tells you, okay, they are in dimension 2, but then they are not going to be same in any sense. So you need to attach further invariants. So the first invariant, I think it was a few centuries ago. So this was the Euler characteristic class. So this is taken to be the alternating sum of the number of cells in each dimension. So that's the number alpha sub k. So that is the Euler characteristic class. So this is again a number you attach to a finite cell complex. So for example, taking a 2-dimensional polyhedron with the number of vertices v, edges, and faces. So you can define the Euler characteristic class. This is the differences, the alternating sum. So for example, for a circle, your Euler characteristic number is 0. So for a sphere, it is 2. For a torus, it comes out to be 0 again. So now this is something, you look at the cell decomposition of your space and you can attach these invariants. But now most often in geometry, your topological space, it has additional structures. So this is what we call as a manifold structure. So why manifold structures are important is because when you want to look at spaces, say for example, you are looking at Euclidean spaces, and we have seen a lot of talks last few days on looking at studying differential equations on Euclidean spaces or on Heisenberg groups and so on. And so you want to carry all those calculus or the differential equations, study of such equations on manifolds. So that means on spaces which don't look like any part of like an open dense subset of your Euclidean spaces. So for example, you have a sphere, you have a torus, and you have higher dimensional analogs, which we want to call as manifolds. And we want to do calculus on such spaces, do integration, do differentiation, study differential equations on such spaces. So for that reason, we want to look at such spaces and we want to put a nice smooth structures. and try to carry forward the technology to such spaces. So in that context, the first thing what people noticed is that the basic invariant, the Euler characteristic number, so it is also defined or it is also realized as the number of zeros of a smooth vector field on your manifold M. So now you have a topological space, you put a smooth structure, a manifold structure, and once you have a manifold structure, you can define vector fields on them, and you look at the zeros of that, so that's a number, and that is again the topological invariant you started with. So you realize that this invariant, it is independent of the smooth structure you put on your space. So this is very interesting. And so this can be generalized. And so more generally, you take, instead of a single top vector field, look at a bunch of vector fields, take the intersections of them. So that defines a homology class. So this is called as a Stiefel-Whitney class. So in particular, you start with a manifold. So that means on a topological space, you have a manifold structure. You get a bunch of invariants. So these all lie in the homology theory of your manifold with Z mod 2 coefficients. So you, in fact, not just get one single number or an invariant, but a bunch of invariants associated to your manifold structure. So your Euler characteristic class, it is also realized as the integral of the top Stiefel-Whitney class. So in particular, your Euler characteristic class, it is determined by the smooth structure. So what we want to do, or rather what we want to understand, is how do you generalize all these further? So in particular, Whitney, he considered vector bundles on topological spaces, not just topological, but actually on manifolds, and try to associate invariants to such vector bundles. So let us look at the basic invariants, the topological invariants. So these are the Chern classes. So you start with a vector bundle on a manifold or a topological space. So vector bundle, as you can imagine them to be a family of vector spaces over your manifold. And the basic or the universal vector bundle is actually on the Grassmannian. So your Grassmannian, it is essentially parameterizes subspaces, vector subspaces of a particular dimension inside some large vector space. So on that Grassmannian, so there is a universal vector bundle which classifies, it says that use whatever a point of your Grassmannian parameter corresponds to a vector subspace. So you attach that fiber over that point. So you have a vector bundle on your Grassmannian. So the classification theorem says that you start with any vector bundle on a manifold or a topological space. So there is a map to this Grassmannian where n could be large. It depends on the dimension of your manifold you are looking at. So there is a classifying map so that your vector bundle on M, it is in fact the pullback of the universal Grassmannian, of the universal vector bundle on the Grassmannian. So this is what is a Whitney-Pontryagin theorem. And so what this also says is that, so it suffices to construct topological classes on your Grassmannian, and then you can pull back those classes on your manifold. So this is the first basic construction or the primary construction of topological invariants associated to vector bundles on manifold. So you have to start doing it on Grassmannians. So this construction was done. So you can look at, again, sections of your vector bundle, look at their intersections and so on. And you can construct classes on topological classes on Grassmannians. Or the other way is to look at filtration of your vector space. And then you look at all those subspaces inside your vector space, which intersect the given filtration in particular dimensions. So these is, correspond to your primary classes or the Chern classes of vector bundles on a Grassmannian. And your classifying map says that you can pull back those classes on your M. Okay, so these are the primary classes. So you notice that actually, so this is why it is important to understand, study vector bundles on M, because it is that it gives another way to construct invariants on your manifold. So because if you want to study classification of manifolds, so the first thing is that how do you recognize your topological classes? So that means you have a homology theory abstractly, a cohomology theory abstractly, but then are they realized as classes? Classes in the sense geometric classes coming from vector bundles. So that's why it's relevant to define geometric objects and attach invariants to them. So now the next thing would be, as I mentioned, that these primary classes, so these depend only on the topological structure. We are not worrying about the manifold structure on the vector bundle as well. So now actually we keep track of the manifold structure on your vector bundle and you look at a connection. And then you try to see if you can attach invariants to such a pair, a vector bundle together with a connection. So now how do you think of a connection? So now as we have seen that you can study vector valued. So you start working on a Euclidean space. People have taught us how to study holomorphic functions, but now you can also study vector valued holomorphic functions. So these actually locally you have it, and then you patch them together. So those would be the sections. And now you want a way to differentiate those vector valued functions. And that formula is precisely you can think of as a connection. See, because your manifold is locally just some open balls in a particular Euclidean space. So locally you know how to differentiate functions, but then you need a good formula which you can apply on the whole manifold, so that which you restrict on any such open set, that is basically a differentiation. Okay, so this is how you think of as a connection. And so you start with the bundle together with a connection. And now what is the classical Chern-Weil theory? It says that there is a way to attach cohomological invariants, but these are with complex coefficients. So this is realized as the trace of the matrix given by the curvature form. So this is what so this is in fact in the de Rham cohomology, H2I, in the even degree de Rham cohomology of the manifold. But what we know here is that the de Rham cohomology with complex coefficients, it is in fact the integral, the singular cohomology groups tensored with the complex coefficients. So that is the de Rham isomorphism. So in particular, the de Rham Chern classes defined in this manner, they can be again identified with the topological Chern classes with complex coefficients. So that's a very interesting fact. So it says that even if you add a connection, you don't really get anything new other than the topological Chern classes. So in that sense, even you start this Chern-Weil theory again corresponds to your basic primary Chern classes with complex coefficients. So now what is a flat connection? So a flat connection says that the curvature form is identically 0. So it means that because as I said that your de Rham Chern classes is written as trace of your powers of your curvature form. So once the curvature form itself is 0, so the trace form also becomes 0. So all the primary classes become trivial. So now then I think this was in 1970s. So people started asking for further invariants, higher order invariants for bundles together with connections, which are flat connections. And so what Chern, Chigger, and Simons, so first they noticed is that you now take a family of flat connections. So that means you take a one parameter family. So for each T, you have a path of flat connections. So what does it say? That there is a variational formula which says that you take the difference of the Chern forms at the two ends. So then that is realized as this integral over that path. So now in particular, so this is true for any one parameter family of smooth connections. So in particular, actually, if you take the each member of this path to be a flat member, so at least in degree I at least 2, because if you look at the integrand, so at least when it is 2, so it says that your integrand becomes identically zero. So it basically says that you have a path of flat connections. So when I is at least 2, it says that the Chern forms, so they are all going to be identical. So that means it is independent of a path of smooth connections. But now suppose instead of assuming that it is a parameter of flat connections, just assume it's a path of smooth connections. So this is actually what you get is a degree, odd degree form. So this has a special name in mathematical physics. So this is these are called as the eta forms. And so this eta form, it has lot of relevance. Actually, I don't know why it is so important. I don't know the physics part of it, but it has a lot of attracted a lot of attention, and people want to understand the Chern-Simons theory via this eta form and so on. But at least what, so I had some questions, like something like, what do you do further about eta forms in the algebraic theory? And so at least we want to understand the eta form more in depth. Something like, is there something more, are there more informations carried by this eta form? Because a priori it just says that you have a path of connections, smooth connections, and you get a eta form like this. So is there a way you can attach certain invariants to a path of connections, say flat connections? So what we have done, like the classical invariant says that you have a bundle, you attach primary invariants, you attach, then you look at a pair, which is a bundle together with a connection. You attach the Ramachan classes, which are essentially up to torsion. Again, the primary classes. Now, suppose you have your bundle with a connection which is flat, then you attach what are called as the secondary classes or the Chern-Simons classes. And now suppose instead of just looking at a bundle with a single connection, you look at a path of connections, which you can assume, for instance, flat connections, a path. Are there certain cohomological invariants you can attach to this data? So in fact, this question was posed, and so I was trying to look at ways to attach cohomological classes. So because we are looking at a path, so one would be looking at the product M cross I. So now notice that I is not a manifold because you have at the endpoints, it's a closed manifold. You don't have that, but still there are some calculations you can do. So which is called as the integration along fibers. And so as I said that, okay, you have certain classes. So as was pointed out in the previous talk also, you don't just look at necessarily on the singular cohomology and homology groups, but you have to look at extend your cohomology theories when you want to define invariants or study classes, and try to see when they can be descended to your ordinary homology cohomology groups. So there was this introduction of differential cohomology. So this was introduced again by Chern, Chigger, Simons in 70s. So where they in fact define classes, so which they called as the differential characters for a bundle with a connection. And then they tried to analyze the differential characters for such connections. So now the same we can do it further for the eta form. So that means for a path of smooth connections, and we are able to define classes, the differential cohomology of your product M cross I, and these can be descended down to M as well whenever your connections are flat. And in particular, they don't lie in the odd degree cohomology groups, but they lie in the even degree cohomology groups corresponding to a path, but with C mod Z coefficients. So this is a further generalization or a further step application, I would say, a further application of the Chern-Simons theory. So now this idea, you can say, why do we just look at path of flat connections or a path of connections, but you can also look at any simplex whose points correspond to smooth connections or flat connections. Are there invariants you can attach to that data? So now you can look at a simplicial set formed by sequences of flat connections under the gauge group transformations. So in particular, we are able to attach invariants to a bundle together with a simplex. And one can see that in particular, you can descend it down to the homology groups of the simplicial set, and it takes values in the appropriate cohomology theory, which is in the differential characters. And in particular, if the points correspond to flat connections, you get maps. So the classical theory of attaching invariants, a bunch of cohomology classes, your Chern classes or Chern-Simons classes, to a bundle with a connection, you can extend it further, and not just for a bundle with a connection, but you bundle together with a cycle of in any dimension whose points correspond to flat connections. You can attach a bunch of cohomology classes. So those bunch of cohomology classes in that particular range, so that in particular turns out to be homomorphisms on the homology groups. And but this simplicial set basically is a has its realization, topological realization, as the moduli space of flat connections on a manifold. So in particular, the homology group of this simplicial set basically can be identified with the homology groups of your moduli space of flat connections. And so you get a bunch of maps taking values in C mod Z cohomology theory. So this extends the Chern-Simons construction. So now there are some bunch of questions which I posed. So this basically generalizes the classical questions. So Chigger and Simons raised the following question, that saying that you look at bundle together with a connection. So you get cohomology classes in C mod Z coefficients. So are these classes torsion? So torsion basically means here that they take value in Q mod Z cohomology. So that is an open question, and I think in the smooth projective case, there are results due to Resnikov on that, and even on a compact scalar manifold. But in general, it's an open question. And so the same question you can extend for the higher order invariants. So instead of looking at just classes like this, you can look at maps on the simplicial set and ask whether they take values in the C mod Z cohomology. I think my time is done, so I'll stop here. Thank you.
Questions, comments?
Higher order.
Take the mic.
Right. So higher invariants would mean that, okay, let me explain it on the board. So you just start with a vector bundle on a manifold, for instance. We are attaching the cohomology classes. So these are in the even degree cohomology groups. See, I said this. So now, so the next construction, what we are saying here is that you start with a vector bundle together with a connection on X. So we are attaching invariants. So these are again in the same the RAM cohomology groups. Okay. But these are with complex coefficients. And the RAM isomorphism says that these two are isomorphic once you tensor this with C. And under this isomorphism, these two agree. So this is the first part. And then the second part, what I am extending this further, is that assume that you have bundle with a connection on X and a nabla square, that means it is flat. So the Chern-Simons theory says that you have classes associated to a flat connection in the odd degree spaces, cohomology spaces, but with C mod Z coefficients. Okay. So this is I. And then the reason why one looks at variation of flat connections, that means you are start looking at path of flat connections, is due to the rigidity property. So which says that you have a path of flat connections. So instead of just a single E, you have a path like this. On X. And then what one sees, notices here is that, assume a priori that each nabla-T is flat. So what it says here is that the Chern-Simons classes remain constant. So this is I is at least 2, because if you look at the integrand, so there's an eta form. Right. So this integral is there. So it says that you have that the Chern-Simons classes, so they are rigid, so they remain constant if you vary them in a path of connections, flat connection. So this is at least 2 because of the shape of the integrand there. So but then if you are not assuming, for instance, that it is flat, but only the endpoints are flat. And now actually it says that this form eta form, so that's a differential form. So is there because see what we are doing here is the Chern-Simons theory says that the Chern form, that's a differential form, it can be lifted as a cohomology class in the odd degree classes. So you have another form, which is the eta form. So that's a differential form. Can you lift it as a cohomology class in 1 degree less? So from 2i minus 1, can you go to 2i minus 2? So corresponding to such a path here, we are able to attach classes. Not just a single member, but this path. So this is in H 2i minus 2. So this is in water. So then the degrees you have to be a bit careful, something like 3 or so. So you can attach invariants. And so the question here is that now suppose if all these classes, you look at a simplex, maybe a path is a 1-dimensional simplex, but now you look at a 2-dimensional simplex. And now suppose the eta forms become trivial. So there is another rigidity property. Is it possible to lift it further? And you can iterate this process. And that's why you get maps like this on the simplicial sets. Okay, so that's the philosophy, constructing maps. And it says that your classical construction, you think of as maps on the 0th degree homology groups, H0, but you can extend them to higher dimensional homology groups. Okay, so that's the.
And what's that map? How does that look like?
So for each you start, so that requires some work. I'm just stating the theorem. So for each simplex you do that, and then you want to organize them together so that if you take a cycle of simplices, and then there is some formula, and which says that it is a cycle in the homology sense. So that will descend down to the homology. Okay, I think I'll give a reference. Maybe you can.
Yes.
Any other question, comment? If not, let's thank Jaya.
Yeah.
Meet at 10:50 for the next talk, which is about 6 to 7 minutes.